Hey guys, today we're going to learn about parallel circuits. So a parallel circuit is a circuit that has multiple paths of travel for electrons. The electrons get to make choices. They get to choose which areas of the circuit that they travel through based on the resistors that are present. So parallel circuits have options. Every time you add a resistor to a parallel circuit, it actually becomes much more easy for an electron to travel. I know this sounds kind of weird, but think about a fire drill. When we have a fire drill at school, if a single door is open, it's very difficult to travel through that single door, and it takes the entire school population to go back inside quite a bit of time. But as soon as someone opens up a second or a third door, the flow of students travels through at a much faster rate. The same thing works for electrons. As you open up more paths of travel to choose to go through, you can travel through them at a faster rate. In order to determine characteristics, just like with series circuits, we have to simplify the circuit a little bit. This means that we have to calculate the resistance if only one resistor is present. Now we're going to calculate it in a slightly different way, so make sure you pay attention. Equivalence resistance is the total resistance present in the circuit. It's the total number of ohms that a resistor would have in order to replace all the resistors present in the circuit. But in parallel circuits, we calculate this by adding the inverse of all of the resistors. So in this equation at the bottom, we have 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus ... to 1 over Rn. Because just like in the past, we can have as many resistors as we want in this circuit. As the resistance decreases, the current increases because the voltage supplied to the circuit remains the same. So as we add multiple paths of travel and our total resistance goes down, our current or our speed of electron travel goes up. So now we're going to do a couple examples just like we did with the series circuits. In this first practice problem, I want to do 1 over Req equals 1 over 17, my first resistor, plus 1 over 12, my second resistor, plus 1 over 11, my third resistor. So 1 over Req is equal to 0.058 plus 0.083 plus 0.09. Now you do want to take that out for a couple decimal places because it will affect your rounding later. So 1 over Req is equal to 0.231. Now when we look at this, this is not our equivalent resistance. We still have a numerator above that fraction bar. So in order to get our Req by itself, we actually have to inverse both sides. And when we do that, our Req has a value of 4.33. So I'm going to plug in 4.33 here. Now, using V equals IR, I can solve for the total current traveling through my circuit. My voltage across the battery is 60. My resistance is 4.33. So I divide those out, and I find out that my total current is 13.85 amps. Okay, now I'm going to look at the diagram real quick. If my electron leaves the battery and travels through the first resistor, it goes back to the battery straight away. If it leaves the battery and goes through the second resistor, it goes back to the battery right away. If it goes through the third resistor, it goes back to the battery right away. They cannot go back down and travel through a second or a third resistor once they go through the first. So since I picked up 60 volts of energy at the battery, and I only travel through one resistor at a time, I must drop all 60 volts at that one resistor. So the electrons going through the green line drop off all 60 volts at the first resistor. The blue line drop off all 60 volts at the second, and the yellow line all 60 volts at the third. Now I'm going to use V equals IR to calculate the current. So my voltage is 60, my resistance is 17. 60 divided by 17 is 3.53. 60 divided by 12 is 5, and 60 divided by 11 is 5.45. Now if I add these three numbers up, I get 13.98. That's slightly bigger than that 13.85, so that's just a rounding issue, and that's completely acceptable. So just like on the series circuits, I'm going to star something here. Your star is all voltages must equal the battery, because you are going through one resistor only. All currents must add to the total. If my total current is 13.85, I must have a portion of that traveling through the first resistor, the second resistor, and the third resistor. So my individual currents must add up to the total. So these are actually backwards compared to series circuits. We said the exact opposite when it came to those. So keep in mind that these are going to be treated a little bit differently. So we're going to do one more problem. Again, I'm going to do 1 over REQ equals 1 over 11 plus 1 over 6 plus 1 over 5. And 1 over REQ is equal to 0.09 plus 0.1667 plus 0.2. 1 over REQ is equal to 0.4567. Inverse both sides, and REQ is equal to 2.19. So that value is going to go here. Now again, looking at the diagram, since my electrons only travel through one resistor and I get 12 volts of energy from the battery, I can place a 12 in each of these boxes. Now I can use V equals IR to calculate each current. So 12 divided by 2.19 is 5.48. My total current is 5.48. That means these three values must add up to 5.48. 12 divided by 11 is 1.09. 12 divided by 6 is 2. And 12 divided by 5 is 2.4. So again, we used this equation to solve for each of the I values. And when we add these three up, we have 5.49, which is pretty close to our total current of 5.48. So we learned series circuits when every atom had to travel through the same path, add up the resistances to find the REQ, solve using V equals IR. Here we learned every electron can choose their path, calculate the resistant equivalent by using the inverses, and then use V equals IR to solve for the unknowns. So we're going to practice with just parallel circuits for a little bit, and then we're going to introduce combination circuits. So I'll see you in class so we can practice.